Inferential statistics allow researchers to estimate unknown population characteristics from sample data. Because observing every member of a population is usually impossible, researchers rely on samples. That means that we have to make inferences about the population using samples of the people in those groups. Inference always includes uncertainty. The size of uncertainty depends largely on sample size and the strength of systematic effects relative to random variation. Larger samples generally reduce uncertainty and improve precision. Researchers seek valid conclusions about broader populations, making careful sampling and measurement essential before statistical testing occurs. A population is the complete group of interest, while a sample is the subset actually observed. Population values are called parameters. Sample values are statistics. Researchers rarely know true parameters, so they estimate them using sample statistics. A point estimate is a single best estimate of a population parameter, such as a sample mean. Because samples vary, point estimates are rarely exact. Understanding the distinction between parameters and statistics is central to statistical inference. When we calculate a sample mean of 18.4, for instance, that value serves as our point estimate. It is our single best guess for the population parameter. But is the true population average exactly 18.4%? Almost certainly not, because every sample contains sampling variation. Relying on a single number is incomplete. We need a rigorous method to quantify and communicate uncertainty surrounding our estimate. Confidence intervals improve upon point estimates by providing a range of plausible values for a population parameter. The chapter illustrates a sample mean depression score of 18.4 with a 95% confidence interval from 17.1 to 19.7%. Researchers typically report 95% confidence intervals because they communicate both an estimate and its uncertainty. Narrow intervals indicate more precision, whereas wider intervals indicate less precision. Confidence intervals help readers interpret results more meaningfully than a single number alone. Error bars are graphical representations of uncertainty around a statistic. They are commonly based on standard errors or confidence intervals. The bars show that a sample mean is only an estimate and may vary if another sample were collected. Shorter error bars indicate greater precision. Longer bars indicate more uncertainty. The illustration compares depression scores for low-stress and high-stress groups and visually communicates uncertainty around each estimate. Hypothesis testing begins with a research question and a prediction. The null hypothesis states that no real difference or relationship exists in the population. The alternative hypothesis states that a difference or relationship does exist. Researchers collect evidence and evaluate whether it is strong enough to reject the null hypothesis. The chapter uses stress and depression as an example, asking whether highly stressed students have higher depression scores than less stressed students. A p-value measures how surprising sample results would be if the null hypothesis were true. Think of flipping a coin 20 times and getting 16 heads. If the coin were fair, getting 16 heads is extremely unlikely by chance. The p-value measures exactly that probability. Smaller p-values indicate stronger evidence against the null hypothesis. The chapter uses a coin flip example and a stress versus depression example to explain this concept. Importantly, p-values do not prove hypotheses, measure practical importance, or establish causal relationships. They are one component of evidence that researchers must interpret alongside theory, study quality, and effect size. In the social sciences, we typically set our significance cutoff or alpha level at 0.05. As shown in our stress and depression comparison table, When the p-values falls below 0.05, we reject the null hypothesis and declare the difference statistically significant. If p is 0.05 or greater, we fail to reject the null, meaning chance variation cannot be ruled out. It is crucial to understand what p-values can and cannot do. A p-value simply indicated whether an observed effect is unlikely due to chance, but it does not measure effect size or practical importance. In contrast, confidence intervals reveal both statistical significance and the actual range of effect size in meaningful units. That's why reporting confidence intervals alongside p-values is best practice. Always remember that statistical calculations are only the final step of a rigorous process. Before calculating statistics, we must establish a clear sampling frame, such as a student directory, and execute sound sampling to minimize error and bias. The estimation of statistics is the icing on the cake. If our initial sampling frame or execution is flawed, statistical inference cannot fix the underlying bias. The chapter concludes that statistical inference uses sample data to make informed conclusions about populations. Confidence intervals quantify uncertainty, hypothesis tests evaluate competing explanations, p-values provide evidence against null hypotheses, and statistical significance guides decisions. These ideas prepare you for future statistical methods including t-tests, chi-square tests, ANOVA, and regression. Across all methods, the core logic remains the same. Evaluate evidence and determine whether the sample supports conclusions about the wider population.